Hey guys, Mr. B here. In this video, we're going to be going over the practice problems in chapter 11.2 on speed and velocity. So let's begin here with number 1. It says Todd drives 55 miles in 1.4 hours. What is his average speed? All right, so we had an equation in the notes that told us how we calculate average speed, and it is total distance. So we can go average speed equals total distance divided by total time. So the distance that he travels is 55 miles. The time is 1.4 hours. All we're going to do is just a simple division problem, and that will tell us what his average speed is. So 55 divided by 1.4, we get 39.2 or 3, depending on how we want to round, miles per hour as our final answer. We'll unbold that. All right, there we go. Okay, number 2, Liz is driving to Tucson, or Tucson. I think this is actually misspelled. There we go. Anyway, so she's driving to Tucson at 65 miles an hour, and it is 275 miles away. How much time will it take her to get to Tucson? So we're just going to basically plug in the numbers that we have into our speed equation. Again, speed, whether it's average or instantaneous, is basically distance divided by time. And they're giving us our speed in this case, so it's going to be 65 miles per hour, which is equal to distance, which we know is 275 miles, divided by time, which we don't know. That's what we're trying to solve for. So we do have to do a little bit of algebra here, which I don't know how comfortable you are with algebra, but if we rearrange some variables. So we need to get time out of the denominator. To do that, we're going to multiply both sides by time. So just times the variable time, basically multiply by the variable time, which seems strange, but that's just what we're going to do. When we do that, then this variable of time is going to go away. So we'll basically get time multiplied by 65 miles per hour equals 275 miles. And then from here, to get the variable time by itself, we're going to divide both sides by 65, let's do it in parentheses, 65 miles per hour. So we'll divide this side by 65 miles per hour. And then these two will go away. They'll cancel out with each other. And so we basically are going to end up with, let's make this font a little bit smaller just so that way we can actually fit all this in here. There we go. So we're going to end up with time is equal to 275 miles divided by 65 miles an hour, which then if we do that on a calculator, we get 275 divided by 65, we get 4.2 hours. So that is the total amount of time that it will take for her to get to Tucson. There you go. All right. Number 3, the SI units for speed are. Okay, so remember that we do not use our usual US units here because we're dealing with the metric system. So it is going to be meters per second. That is the SI unit for speed. Number 4, how is instantaneous speed different from average speed? So remember that average speed is your speed over typically a very long trip or a longer duration. And instantaneous speed is your speed in a very, very short amount of time, or basically a moment in time. So we'll say that instantaneous speed is your speed in a moment or particular instance in time. And average speed is your speed over a long duration. Something like that. And you can go back and use the definitions from the notes if you wanted to, but I always like to put answers in my own words just so that way I have a better understanding of what they mean. So, all right, number 5, the equation used for calculating average speed is, oh, we wrote this one down already. So we know that average speed is equal to total distance divided by total time. Okay, and that again is the previous slides right there. Okay, number 6, true or false. You can determine how fast you are going at the midpoint of a trip by calculating average speed for the entire trip. No. You cannot determine your average speed, or you cannot determine a particular point in a trip using average speed, because the average speed is the whole trip. So if you wanted to know how fast you're going at the midpoint of a trip, you'd need to know your instantaneous speed. So that is false. Or instantaneous speed at that particular point. So number 7, a student walked 1.5 kilometers in 25 minutes, and then realizing he was late, ran the remaining 0.5 kilometers in 5 minutes. Calculate his average speed on the way to school. All right, so average speed is, again, total distance divided by total time. And in this problem, we have 2 distances and 2 different times. So we need to add the distances together, add the times together, and then divide them to get our average speed, which will be in kilometers per minute. So we're going to have 1.5 kilometers plus 0.5 kilometers, which is equal to 2 kilometers. This is our total distance. And then as for our time, we're going to have 25 minutes plus 5 minutes, which is going to be 30 minutes. That's our total time. I think it said this is total distance, total time. If I said total time before, slip of the tongue. So our average speed is total distance divided by total time. So average speed is equal to 2.0 kilometers divided by 30 minutes. And let's see what we get. So 2.0 divided by 30. We get 0.067 kilometers per minute. Okay, the unit's going to be kilometers per minute, which is sort of a weird unit because you usually measure things in like kilometers per hour, but it is what it is. So anyway, all right, moving on. Number 8, the slope of a line on a distance time graph represents what? So this also is directly from the notes, but is this slide right here. The slope of a line on a distance time graph is speed. So we can find the slope of a distance distance versus time graph. That will tell us the speed of our object. All right. Number 9, draw a point on the graph that represents 200 meters traveled in 4 seconds. Draw a line connecting the point with the origin. Label this A. Okay, so we're going to go insert line arrow. Let's do line, I guess, line. So we're going from 0 to 4, in 4 seconds to 200. Okay, so it's going to be 4 seconds, 200. So we're basically going to go right there. Okay, there's our line. And then we're going to go insert text box. And we'll put a text box right there. And we'll label this line A. Okay, so there's line A right there. Bam. Okay. I think there's another part to this problem. So it says number 10 on the previous graph, draw a point that represents 100 meters traveled in 10 seconds. Draw a line connecting that point with the origin and label it as line B. Okay, so 100 meters in 10 seconds. So let's again go to insert line. So 100 meters, 10 seconds is here. 100 meters is right there. So we're going to draw a line and connect it to our origin. And then we will go insert text box. And we'll label this line B. Okay, so here's line A and line B. Okay. And then number 11 says calculate the average speed or the slope of lines A and B. So they just want us to find the slope of line A and line B. All right, so to find slope, we're going to take the vertical change divided by the horizontal change. Okay, so basically we'll go from the origin here at 0, 0, and then we'll go to the tip of the line at line A. So vertically it goes from 0 up to 200, and horizontally it goes from 0 over to 4 seconds. So for line A, again we'll change our font colors here. So we'll go line A slope is going to be equal to 200, and the units I believe are meters. So 200 meters divided by 4 seconds. Okay, so it's rise over run, or vertical change divided by horizontal change. So 200 meters divided by 4 seconds. So let's see, 200 divided by 4 is 50. And that will be in meters per second because meters divided by seconds, that's the units that we get. And then for line B slope, this one, line B, vertically goes from 0 up to 100. So vertically it goes up 100. Horizontally it goes from 0 to 10. So our slope is going to be 100 meters divided by 10 seconds. And we'll see what we get here. So 100 divided by 10. 100 divided by 10. There we go. We get 10 meters per second for that slope. All right. Question number 12. How do speed and velocity differ? Okay, so speed and velocity are similar, but they are different. And the difference is really simple, basically. Speed doesn't include direction and velocity does. So that's all we're going to say. So we'll say that speed does not include direction and velocity does. So that's the only way that they're different. Number 13, circle the letter of each sentence that describes a change in velocity. Okay, so remember that velocity is a vector. It's speed with direction. So any change in speed or any change in direction will be a change in velocity. So that means that letter A, an object, a moving object gains speed. We're changing speed. That's a change in velocity. A moving object changes direction. That's a change in direction. That's a change in velocity. A moving object moves in a straight line at a constant speed. Okay, so it's not turning, it's not changing direction, and a constant speed means it's not slowing down or speeding up, not a change in velocity. And then letter D, a moving object slows down, so that is a change in speed. That's a change in velocity. Okay, last two questions here. Number 14, how do velocities combine? So remember that velocity is a vector. So when we have multiple velocities, we can combine them using vector addition. And again, there's a slide right here that even says 2 or more velocities add by vector addition, and they even give you some examples. So we'll basically say that 2 or more vectors combine by using vector addition. Okay, and then lastly, number 15, a river flows at a velocity of 3 kilometers per hour east relative to the riverbank. A boat moves upstream west at a velocity of 15 kilometers per hour relative to the river. What is the velocity of the boat relative to the riverbank? Okay, so this sounds like a really strange and difficult question, but it's actually pretty simple. So first we're going to insert an arrow, and we're gonna do the river. Okay, so river flows at a velocity of 3 kilometers per hour east. Relative to the riverbank just means that it's moving at 3 kilometers per hour relative to the ground, which isn't moving. So it's just telling us the speed of the river. So we're going to draw an arrow. Let's just draw an arrow this way, going east, and we will insert a text box, and we will label this as 3 kilometers per hour east. And this is the river. Okay. And then we have a boat, which is moving west at 15 kilometers per hour relative to the river. So that means that if it's relative to the river, we have to take into account, actually, you know what? No, we're just going to draw a vector that's 15 kilometers per hour going west. Sorry. Don't mean to confuse you. I'm going to just confuse you. So, all right, let's draw an arrow. It's going to be a longer arrow because it's 15 kilometers per hour rather than 3, so it's a bigger vector. So I'll do text box, and we will write 15 kilometers per hour west. This is the boat. Okay. So here are our 2 vectors, and the question is what is the velocity of the boat relative to the riverbank? So basically it's saying if you are standing on the side of the river on the ground and you're watching this boat, how fast is it going to look like the boat is moving? Now, you might think, well, it's going to be moving 15 kilometers per hour, obviously, Mr. B, because it's what it says in the problem, right? Okay, but remember, it's moving upstream. So there's a river that is pushing against it, which is going to slow it down. And even though the boat captain, if he looks at his little speedometer on his boat, it might say 15 kilometers per hour. For people that are watching them, that are on the shoreline, watching this boat try to go up the river, upstream, the boat's going to look like it's going slower, right? Because the river is going to be slowing it down. So all we're going to do for this is just subtract these two vectors. We have a velocity going west at 15 kilometers per hour. We have a velocity going east at 3 kilometers per hour. These are opposite in direction. Since they're vectors, we can just subtract them from each other. So basically, we're just going to take 15 kilometers per hour and subtract 3 kilometers per hour. And that will give us our velocity of the boat, basically. So it's actually just a basic subtraction problem. It's pretty easy. Okay, so 15 kilometers per hour minus 3 kilometers per hour equals 12 kilometers per hour. And of course, we have to include a unit. So a direction. So what direction is the boat going to look like it's traveling in? Well, originally it looks like it's traveling west at 15 kilometers per hour. The river's pushing on it east. You know, the boat's still going to be traveling west. It's just going to be traveling slower because the river's slowing it down. So our final answer is going to be 12 kilometers per hour west, because that is the direction that the boat is traveling in. Okay, but that is our answer. That's how fast the boat's going to look like it's moving relative to the riverbank, because the river's slowing it down. So, okay, hopefully that made sense. Just some basic vector addition, vector subtraction. But if you have any other questions, as always, you can email me or talk to me in class, or we can do some one-on-one tutoring, and I can help make sure you understand this stuff. So, all right, guys, thanks for watching. I'm Mr. B. See you in the next one. Bye.